In this section, we will revisit something you've already done, and that is solving polynomial and rational inequalities. We did that in section 1.8. We did it again a little bit when we were studying polynomials and rational functions. We're going to look at some more examples, and you might see some strange looking solution sets with unions of intervals and single numbers and sets. So we'll just go over those steps again and look at some more examples. So before we made those big sign charts, one row for each factor, and we had to do a lot of work to test all those numbers in each of those subintervals, and you kind of have to go through that to have a better understanding of how these inequalities work. But now that you do, you can use these shortcuts because now we know about multiplicity and end behavior and how the zeros affect what the behavior of the function is around those zeros. So here are the steps. The first few steps are exactly as before. Move all the terms to one side, make the other side 0, put everything in order, ready to be factored. If there's more than one fraction, combine them all together into one fraction, and then completely factor everything on the left. If it's a rational expression, completely factor the top and the bottom. Then we're going to find those critical values, which we can now just call the zeros of top and bottom, and put them on a number line. And then you can either use a test number for that interval that's furthest to the right, the one that goes to positive infinity. Or you can look at the leading coefficient and the leading term, because that tells you whether that last sign furthest to the right is going to be positive or negative. And then all we really need to know is, as we move along the number line from right to left, from numbers, the biggest numbers, towards the smaller numbers, how does that sign change, or does it change? How does the sign chart look? And that has to do with the multiplicity. So as you go, you get to a 0, you have to look at its multiplicity. If it has odd multiplicity, which means it came from a factor that was to the first power or the third power or the fifth power, then remember that that behaves like a line or a cubic or fifth degree, and it goes through the x-axis, which means the sign changes. But if it root has even multiplicity, if the 0 has even multiplicity, so that means it came from a factor that was to the second power or fourth power or sixth power, etc. It means it bounces off the x-axis. And that means the sign isn't going to change. If it was positive, it stays positive. If it was negative, it stays negative. So you get the same sign. And then you're trying to solve an inequality which has 0 on one side. So you either have greater than 0, less than 0. They all have to do with the sign of the expression. So you just have to read the correct solution off of your sign chart to see which ones make the inequality true. Let's look at some examples. So the first step for this one, there's nothing to do because we already have 0 on one side. And the second step doesn't apply because there are no fractions. The third step, we already have everything factored out here, so we don't have to do anything there. So we're just going to list the zeros, list their multiplicities, and then put them on a number line in order. Zeros of this is basically what we also called critical values when we were doing this in the earlier chapter. So each factor gives us our zeros. The negative 2x to the fourth gives us 0. X minus 2 gives us 2. X plus 3, negative 3. And x minus 5 gives us 5. Let's also list the multiplicities of each of these zeros. 0 came from x to the fourth, so it's a root 4 times. It's a 0 4 times. That's its multiplicity. X minus 2 is just to the first power. So 2 is just a root 1 time. Negative 3 came from x plus 3 cubed, so its multiplicity is 3. And x minus 5, again, is just to the first power, so its multiplicity is 1. Let's put these zeros on a number line in order from smallest to biggest. So negative 3, then 0, then 2, then 5. Now we are going to figure out the signs instead of making one row for each of these factors and have this big sign chart. We're just going to figure it all out on this one number line. And first sign that you're going to figure out is the one for the biggest numbers, because that matches your leading term sign, your leading coefficient. Now, if you don't want to figure out, if you're afraid you might get the wrong answer for the leading term, you can just pick out a number, do a test number, like pick out 10 or something bigger than 5, and plug it in each factor. You're going to get a negative 2 times a positive, 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 positive. So negative 2 times those positive numbers is going to be negative. If you want to practice also finding the end behavior based on the leading term, you can do that just to practice what we've learned in previous sections. The leading term is that negative 2x to the fourth. It gets multiplied by x to the first power times that x is going to get cubed when it gets expanded times that x to the first power. So that is negative 2x to the 4, 5, 8, 9th power. And we know the behavior of that. It kind of looks, the end behavior is like a negative x cubed. So on the left it goes up, on the right it goes down. See, it goes down. It's negative as x goes to infinity, which, yes, confirms that we do have a negative sign right there. So now all you have to do is figure out, as you hop over each of these zeros, does the sign that you have before change or does it stay the same? So that is what you have in your instructions. As you move along the number line to the left, the zero that you're passing, does it have odd multiplicity or even multiplicity? Remember, odd goes through, it becomes the opposite sign. Even stays even Steven. It bounces off the x-axis, it stays the same. So 5 has multiplicity 1, it's odd, which means the sign is going to change. Your graph would go through the x-axis. If it was negative here, then it's going to become positive here. Then you look at the next number, 2. The multiplicity of 2 is 1. Odd multiplicity, change, opposite sign. Then 0, its multiplicity is 4. Even multiplicity, even Steven, don't change it. Then negative 3, multiplicity is 3. Odd, opposite sign. Negative becomes positive. So now we know the behavior of this expression everywhere on the number line, and we're looking for greater than or equal to 0, which, remember, means we look for in our sign chart positive and 0. That's where our solution is going to come from. Greater than 0 and equal to 0. So the greater than 0 is everywhere you see plus. But equal to 0 is actually all the zeros of this polynomial. So also at negative 3, 0, 2, and 5, you want to make sure you include all of those numbers. So what would that solution set look like? We go from negative infinity to negative 3, and we want to include negative 3. Union, you might want to just use the next plus that you see, which is all the numbers between 2 and 5, including both 2 and 5. But if you leave it there, you're missing one number in your solution set. Can you see what number is missing? Right there. 0 is also a solution to this inequality. We highlighted it because it gives us 0 and 0 is included here. So this is how you write that, union, and then it's what we call a singleton, a set with just one element in it in this case. The set including just 0. So this is the solution to this inequality. Let's see another example. Here's an example of a rational inequality. We're supposed to move all terms to one side, which we already have, 0 on the other side. Then if you have more than one fraction combine into one, we already have only one fraction, everything is factored. So we're ready to find the zeros of top and bottom, which again we also call the critical values of this expression. So the zeros are, from the top, we have 0, -3, and from the bottom, when 2x plus 9 is set equal to 0, we get -9/2 and 6. Now for the multiplicities. 0 came from x to the 5th. The multiplicity is 5. You might want to just write odd and even if you don't feel like writing out the exact value of that multiplicity. So -3 came from x plus 3, which is to the 4th power. I'll just write the multiplicity for now. And then -9/2 came over here to the 3rd power. And 6 came from over here. It's just to the 1st power. So we will write these on a number line in order. -9/2 is -4.5. That's less than -3. And then 0 and 6. Start with the biggest numbers towards infinity. That's the end behavior in that direction. You can either look at your leading coefficient, your leading term on top and bottom, or you can just pick a number in there to plug in to see if you get positive or negative. But we have to have that starting sign. So let's say we plug in, I don't know, something bigger than 6, like 10. Plug it in here, you get positive, 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 positive. So that's a positive. And then you say, okay, as I hit 6 now, 6 is a value that's a critical value here for this expression. Either the sign is going to stay the same, plus, or it's going to change to minus. Which one is it? For that, we'll look at the multiplicity. The multiplicity is 1, which is odd, so the sign changes, opposite sign. And you do the same thing for the next number, 0. 0 has multiplicity 5, odd, so you write the opposite of this sign. It becomes plus, it changes. -3 came from here, even multiplicity, so plus, even Steven, stays the same. -9/2 has multiplicity 3, odd multiplicity, you write the opposite of the sign. So the sign that we're interested in, this is the inequality we're trying to solve, is less than or equal to 0, which means we are looking for negative and 0. Well, not all of these numbers are going to give us 0. Remember, any 0 on the bottom is bad, so we don't want to ever include those. We do want to include the zeros of top, which are 0 and -3. So let's write out what this set is going to be. Everything that you see highlighted, I see a negative there, so -infinity to -9/2. We do not want to include -9/2 because it gives us 0 on the bottom. Let's write the other negative interval. That's from 0 to 6. We do want to include 0, see it's highlighted, but we do not want to include 6 because it makes the bottom 0. There's one other number that we're missing here, that -3 is also part of the solution set because it gives us 0 on top, which is what we want. So remember, we write it as union -3 just by itself in a set. Here's one more example. We have a rational inequality, but we do not have 0 on one side. So we do have to make one side 0. We subtract 1 from both sides to get 0 on the right-hand side. But as you can see in step 2 here, if the left side has fractions, then combine into one fraction. So I can't really make a sign chart for this until it's one fraction and factored on top and bottom. So for that, we will find the common denominator, which is just x squared minus 2x minus 3. And we multiply top and bottom of this by that common denominator. So they will both now have x squared minus 2x minus 3 on the bottom. But the new top here would be the top of the first fraction minus 1 times that common denominator. Make sure you put this in parentheses. The negative 1 is going to have to distribute to all of that. So let's simplify this. Distribute that negative 1. Again, if I'm going to factor this, I have to simplify it all out. Oops, this is a plus. Forgot to distribute that minus. So the negative 2x and the 2x go away, and we get 1 plus 3 is 4. You can write this as 4 minus x squared or negative x squared plus 4, either way. So this was all step 2, combine into one fraction. Next, we are going to completely factor that left side. Factor the top, factor the bottom. So 4 minus x squared, difference of squares, I can write it as 2 minus x, 2 plus x. And x squared minus 2x minus 3 can be factored into x minus 3, x plus 1. And we are looking for greater than or equal to 0. So we just did this step. Then we are going to find all the zeros of top and bottom and put them on a number line. The zeros of top and bottom are 2, negative 2, 3, and negative 1. And then their multiplicity for all of them is just 1. This one's easy in that sense because we don't have to worry about whether or not the signs change. They will change. All the signs alternate as you go through those zeros. So let's put them on a number line. Negative 2, negative 1, 2, 3. Now, always start with this one when you're doing it this way. So we already drew our number line. Now we are going to use a test number to figure out the overall sign for the interval that's furthest to the right. So either do it with leading terms on top and bottom, or with just a test number like 3. I don't know, something bigger than 3, 100. Pick a number that you know for sure is going to be in that interval. So 2 minus 100 gives you negative. Then 2 plus 100 gives you positive. 100 minus 3 gives you positive. 100 plus 1 gives you positive. The overall sign of that is going to be negative. All of these zeros have odd multiplicity, just 1, which means then as you go through each of those zeros, the sign will become opposite of what it was on the other side of that 0. The signs will alternate. Greater than or equal to 0 means we are looking for positive and 0. What gives us 0? Whatever makes the top 0, which is negative 2 and 2. So let's write these intervals, these sets. Our solution to this inequality will be, we want to include negative 2 all the way to negative 1. Do not include negative 1. That's a bad number. It gives a 0 on the bottom. Union 2, bracket next to the 2, but parentheses next to the 3. And that is a solution for that inequality. So really what you have to remember once you solve these inequalities using these shortcuts is how to determine what multiplicity your zeros have and how that affects the sign chart. Odd multiplicity, change the sign as you move through that 0. Even multiplicity, keep it the same.